Good evening, ladies and gentlemen. This is Professor David J. De Los Reyes. The date for tonight is May 5, 2025, and the time is 21:37. That's military time, so it should be 9:37 p.m. My topic for this evening will be a continuation of my long video format topic, DC circuit, and I am now on lesson number 32. Lesson number 32 is actually the same as lesson number 30 and 31, meaning the same. We will be solving the same problem. So lesson number 32 will now be the third marathon solution for lesson number 30. Okay, let's proceed. The subject matter for tonight will be a long video format topic, and the title of the topic will be Direct Current Circuit, lesson number 32, and the title of the topic will be Series Parallel Combination Method of Solution. Lesson number 32 is the same as lesson number 30 and 31, meaning the problem we are solving for tonight will be the same as 30 and 31, and the main concentration of the concept that I will be emphasizing is that we will be solving one problem and we will bring out a marathon solution. This one for tonight is actually the third solution by using the so-called series parallel combination. Okay, let's try to bring out the problem. The figure for lesson number 32 will be the same as for lesson number 30 and 31. So this will be the given figure. Okay. The given circuit is this one. This is an 18 volt. This is 2 ohm. This is 4 ohms. This should be closed circuit. This is 6 ohms. This is 8 ohms. Okay. The requirement for this problem is that we must have to solve for the current passing through this 8 ohm load here, if the applied voltage is actually 18 volts. So the one with an arrow placed in the red pen, this is capital letter I with the subscript O, meaning what will be the current passing here with this given configuration. So what is being asked is actually the current passing through this 8 ohm load here. Using the marathon solution, it will now be the third type of a solution. That is by using the so-called series parallel concept. I will try to bring out the answer for lesson number 30 and 31. Actually, they are the same. And supposedly what will come up for tonight will be the same as for 30 and 31 because we are solving the same problem. The current passing through the 8 ohm load by using the two marathon concepts of solution, that is by using the Thevenin's and Norton's, it is 1.551 ampere. Using the lesson number 30 is by using Thevenin's solution, and lesson number 31 is by using Norton solution, and the current are the same, 1.551 ampere. So for tonight, we will be expecting that the current will passing through here by using the series parallel combination concept. It is 1.551 ampere. Okay, let's proceed with the solution. Step number 1, we will solve for capital letter R with the subscript T first. Capital letter R with the subscript T, meaning we will be computing for the total single equivalent resistance of the whole circuit. Okay? The main reason why we need to compute for R total is that we must have to compute for I total. So in the computation for the I total, we could compute for the voltage across the 8 ohm load by using that data. And if we could find the voltage across the 8 ohm load, it will now just be a matter of dividing that voltage divided by this 8 ohm, and that will be the corresponding current. Okay, let's proceed with the computation of the total resistance. I will not redraw the circuit. Anyway, the circuit is just a simple one. These 4 ohms here and 6 ohms are actually in series. We will represent that one by RE1, meaning the compressed value of this one. We will represent that as RE1. So since they are in series, the total resistance will be 4 plus 6, and what will come out is 10 ohms. So meaning to say the single equivalent of this is 10 ohms. Okay? The single equivalent of 4 and 6, which is 10, if we try to figure out the circuit, it will be in parallel with this 8 ohms. And again, we could compute for the single equivalent of those two components in parallel. And so, the single equivalent of this one is 4 and 6, that will be 10. And it is in parallel with 8 ohm. So if we try to take the single equivalent, there are only 2 resistances in parallel. And if we are taking the single equivalent, it will be the product all over the sum. First resistance times the second over the sum of the first and second, because they are in parallel. Okay? So what will come out will be the product 10 times 8 all over 10 plus 8. And what will come out will be 4.45 ohms. 4.45. So meaning to say, the single equivalent of this one will be 4.45 ohms. Okay? Let's try to figure out again the circuit. This 4.45 will now be in series with this 2 ohm here. So the total resistance we are to compute will be the sum of 2 ohms plus 4.45, since they are in series. And we will now designate this one as R total, capital letter R with the subscript T, meaning the total resistance of the entire circuit after the 2 simplifications. This 2 ohm will be in series with the single equivalent of this one, which is 4.45. So what will come out will be 6.45 ohms. So after the computation of R total, we could now compute for I total. Because if we try to redraw the given circuit, this is 18 volts. R total is actually 6.45 ohms. Right? So it seems we are now just given a simple circuit in which the applied voltage is 18 volts and the total connected single equivalent resistance is 6.45. So actually we could compute for I total now. I total will be the total current coming from the 18 volt source with this given configuration. And by using the equation voltage equal to IR, current now will be equal to voltage over R. The applied voltage will be 18, and the total single equivalent resistance of this, after 3 simplifications, is actually 6.45. So this is over 6.45. So what will come out for the total current will be 2.79 amperes. So the current emanating from this 18 volt source here will be with the value 2.79 amperes. Okay? We needed this current in the computation of the voltage across the terminals A and B, which is actually equivalent to the resistance across the 8 ohm load. Right? So to compute for the voltage across this, we'll try to disconnect this portion here and this portion, and we'll just take this loop here. We'll redraw this one, so what will come out will be this one. This one. This is the 18 volts. This is the 2 ohms. This is the 8 ohm load. This is where we disconnect, right? Disconnection. So all the details here are actually given now. This is 18 volts. The total current from the 18 volts according to our computation is 2.79 amperes. This is 2.79 amperes. It passes through the 2 ohm load, and upon entering this junction here, there will be a current that will pass through this 8 ohm loads here, and that is actually the one we are looking for, right? So to bring out the voltage across this, we will take the summation of voltages equal to 0. In any closed loop, if we try to take the summation of the voltages, we will equate that to 0. That is actually Kirchhoff's voltage law, right? So if we now try to take the summation of the voltages here, this 18 here is actually a voltage source. This is plus 18. The drop, the voltage across the 2 ohm load should be a voltage drop. So this side here will be negative. Okay, and since voltage is equal to IR, we know the current passing through the 2 ohm load, and we know the value of the resistance, it is 2 ohms. So we could compute for the voltage across this, and which is supposed to be a voltage drop. So this is minus, the current passing is 2.79 times 2, and the voltage across this point here, AV, we will just designate that one for the meantime as a voltage across terminals A and B, and according to Kirchhoff's voltage law, they should be equal to 0. So if we try to notice the resulting equation, the only unknown is actually BAV. And if we try to compute for BAV, BAV will be 18 minus the product of 2.79 times 2. And what will come out for BAV is 12.418 volts. And if we try to go back again to the circuit, the voltage across AB is actually the same as the voltage across the 8 ohm load cell. So I place it here, voltage across terminal AB is equal to the voltage across the 8 ohm load. Okay, and this is actually 12.418 volts. And again, by using the equation voltage equal to IR, we are computing for current. So it should be voltage over R. So considering this question here, the voltage is actually 12.418 and the resistance is 8 ohms. So if we try to take the ratio, what will come out is 1.551 ampere. So the current passing through the 8 ohm load here is 1.551 ampere. It is the same as the current passing through the 8 ohm load here by using the first solution, which is Thevenin's, and by using the second solution, which is Norton's. And the third marathon solution is actually by using the series parallel combination concept. And what comes out is still 1.551 amperes. Okay, that's it, guys. We are just bringing out this marathon solution so we could verify the validity of our answers by presenting marathon solutions. So for those of you who would like to watch my channel is at youtube.com/@ProfDavidJ. If you want to share it, please click share. For those of you who do not know yet that my channel contains long video format topics, my long video format topics, it's a complete syllabus. I got 10 subjects already. It comprises of differential calculus, integral calculus, differential equation, advanced math, AC circuit, DC circuit, algebra, trigonometry, and analytic geometry. Those are my long video format topics. So for those of you who intend to take up engineering, my channel could be a good source of some good academic thing if you would like to take up engineering. And on my short videos comprises of something on electronics because I know how to troubleshoot electronics. I could contribute that one and some other things. That's it for tonight. Good evening from Los Angeles. This is Professor David J. De Los Reyes.